everyone. In today's video, we are going to be talking about fluids and pressure. Now, we're going to tackle this on 4 distinct fronts. The first is we're going to be defining what a fluid are and what states of matter can be considered fluids. We're also going to define what pressure is and how to calculate pressure. We're going to be looking at the factors that affect pressure, and then we're going to be ending with the 3 principles of fluids. So let's get started. Fluids. By definition, a fluid is anything that flows and that fills the space of its container. Now, there are 2 states of matter that can be defined as a fluid, and they would be liquids and gases. Now, a lot of you, when you think of fluid, you think of liquids right away, and then you're wondering, well, why do gases apply? Because if we're looking at our definition of our fluid, the first thing is anything that flows. And both liquids and gases flow. The second is this concept of filling the space of its container. Now, liquids, by definition, because they have weak molecular bonds in between the liquid particles, they fill the space of their container. Now, gases, because they have no particle bonds, they fill up all available space, which would also mean the space of whatever container it is in. So if we take a look at our 2 images of liquids and gases, it also has to do with the degree of particle movement. Because liquids have weak bonds, it has moderate particle movement. So it's moving more than solids, but less than gases. Because gases have no bonds, it has very high particle movement. So high movement due to no bonds, whereas liquids is moderate movement due to weak bonds. Now, one thing that's really important to note is that solids are not fluids. Same thing with granular solids. They are not fluids because they don't flow and they don't fill up all of the space of their containers. Now, the next thing that we're going to be looking at is the definition of our different fluids. Now, what we actually have right here is a syringe that is filled with a gas. Now, if I'm looking at my syringe and if I'm looking at my gas, and so I have my syringe, and what's really important here is this part of the syringe is my plunger. Now, what's really important about gases is that if I push my plunger up in through the syringe, and what's really important to note is that the end of the syringe is capped so that nothing escapes. Because there are no bonds in between my gas molecules, if I reduce my volume, which is what's happening here by pushing in the plunger, my gas molecules will come closer together. And I can see the difference between picture 1 and picture 2. My gas molecules are now closer together. So that means my gases are considered a compressible fluid. In the sense that I can change its volume. It can be compressed. And if I were to do the opposite, so here, so picture A, I had my initial scenario, picture B, I pushed my plunger in. If I were to, and this, in this case, the volume went down. If I were to go the opposite direction by moving my plunger so instead of pushing it in, pulling it out, I would actually be creating more space and my volume would increase, is what I have in picture C. So volume increases and now I have more space. Here I had less space. And you also have to realize that the amount of space that I have between my gas particles also will affect how much my gas particles will hit each other. If I have less space, my gas particles are hitting each other all the time because there's not a lot of place for it to move. If I have more space, my gas particles are more spread out, so it's less likely to hit. So anything that is considered a compressible fluid means that the volume can be changed. And the only thing that is considered a compressible fluid are gases. Now, if gases can be compressible, then liquids are considered non-compressible. So same scenario that I have right here. I have my syringe that is full of my liquid, and I can see from my particles that there's not a lot of empty spaces in between. There are some gaps, but because I have those weak bonds, there's not a lot of empty space. So this I have is my liquid. So down here, liquid. And again, if I try, so here I'm trying to move the plunger, but the plunger is not moving. So I'm applying pressure, but the plunger doesn't move. That means my volume is constant. Now, obviously, if the seal over here closing the plunger broke, well, then my liquid would go everywhere. And even the opposite, if I move the plunger, my volume, and I move the plunger in the opposite way, my volume still stays the same. So this would be considered an incompressible fluid. And incompressible fluids are liquids. And the key thing about this is that the volume stays constant. So now that we've talked about fluids and what are different types of fluids, we're going to be moving on towards our definition of pressure. So pressure is defined as a force applied perpendicular to a surface. Now remember, perpendicular means at a 90-degree angle. So if something is perpendicular, I have a 90-degree angle separating my two surfaces. Now the equation to calculate pressure is equal to force divided by my surface area. So force would be measured in newtons, and surface area, again, because this is area, would be measured in meters squared. So we're going to go ahead and do some practice with calculating pressure. So our first practice question: how much pressure does a box with a surface area of 0.25 meters and a force of 500 newtons exerts? So first thing that we need to do is we need to write down our equation. Pressure is equal to force divided by area. We need to isolate what our variables are. So this 0.25 meters is our area, and 5,000 newtons is our force. Okay, and now we have our equation, we have our variables, we are plugging in. So pressure is going to be equal to 5,000 newtons divided by 0.25 meters squared. And we do that division, so 5,000 divided by 0.25, and we have pressure equal to 20,000 pascals. Straight, simple, to the point. Let's try a next one. Okay, so in question number 2, we've actually kept the force the same, but we've actually just lowered the surface area, and we want to see if this is going to actually make an impact in the pressure that we're going to calculate. So our equation is still the same, that we have pressure is equal to force divided by area. So pressure, again, the force is the same like from the last question, 5,000 newtons. And now our surface area is reduced, and it's now 0.1 meters squared. And when we do 5,000 newtons divided by 0.1 meters squared, we get pressure is equal to 50,000 pascals, which actually makes sense, because if we're looking at our two scenarios and we have the same amount of pressure, so this is the surface area from question number 1, so 0.25 meters squared. This is the surface area from question number 2, this question, 0.1 meters squared. Well, if my surface area is now smaller, that means I have a smaller, more concentrated place for my force to be applied. So if I have a smaller, more concentrated place for my force to be applied, well, I'm going to have an increase in my pressure. Whereas here, this is larger. So it is more spread out. So my pressure is going to be lower. And that's actually out of the two variables that can be altered in our pressure equation. If my surface area decreases, my pressure as a result is going to be increasing. So we're going to do one more practice question, and then we're going to be moving on in our video. So our last practice question: which object exerts a greater pressure? A tank whose road wheels have a combined surface area of 50 meters square and which applies a force of 20,000 newtons. So this is our first scenario. Or a ballerina slipper that has a combined surface area of 0.001 meters squared and has a combined force of 200 newtons. So we have tank over here, and we have ballerina over here. Okay, so for our tank, pressure is going to be equal to our 20,000 newtons divided by our surface area of 50 meters squared. Our ballerina, our pressure is going to be equal to 200 newtons divided by our surface area of 0.001 meters squared. So if we do that calculation for the tank, where we have 20,000 newtons divided by 50 meters squared, we get a pressure of 400 pascals. And for the ballerina, if we do 200 newtons divided by 0.001 meters squared, we get a pressure of 200,000 pascals. This is why one of the common injuries that ballerinas have is breaking their toes, because they have an exorbitant amount of pressure that is being applied to their toes, so their phalanges. So that's why it's a very, very common injury when it comes to ballerinas. Tank, because I have the entire mass of the tank spread out over a very, very large surface area, the overall pressure is quite low. That's why you can have tanks that have masses that are exorbitant, but can still actually go on sand, can go on muddy surfaces and not sink. So what we're going to do is we're going to look at the factors that affect pressure. And one of them we actually did. When surface areas increase, the pressure decreases. And we saw that when we were looking at the calculations for practice question number 1 and practice question number 2. For the second, when forces increased, pressures increase. And we also have to realize that the area is kept constant. And this intuitively makes sense. If I'm applying more force, the amount of pressure is going to be increased. So we're going to do just some quick practice calculation here. So if I have a force of 100 newtons spread over an area of 1 meter squared, well, my pressure is going to be 100 pascals. Now, if I, let's say, quadruple the force, so instead of 100 newtons, it's now 400 newtons, and my surface area, I don't do anything to it, so it's the same, well then, my pressure undoubtedly is going to increase. Okay. Now, one of the things that we need to talk about is the factors that influence pressure exerted by incompressible fluid. And when we're talking about incompressible fluid, we are talking about liquids. Now, the only thing that is really impacted here is mass. The reason why, my volume can't change. If my fluid is incompressible, that means the volume is kept constant. And there's two. The first has to do with the mass of the liquid that is above. So if I have a large amount of liquid on top of whatever object it is, well, the more liquid I have, the greater the increase of the mass of that liquid. So that means I'm applying a higher force, leading to a higher pressure. Now, similarly to the mass of the liquid, the density of the liquid also applies. If my liquid is more dense, that means I have a greater mass to volume ratio, because again, density by definition is the amount of matter that you have per unit volume. So if I have a highly dense liquid, that means I have a liquid that has a high amount of matter. If I have a higher amount of matter, that means I'm also going to be increasing my force, which is leading to increasing my pressure. Now, a compressible fluid is something that can change its volume. And there's only, again, one type of compressible fluid, which are gases. And the key thing is compressible fluids, the volume can change. Now, everything that has to do with the pressure exerted by compressible fluids has to do with the concept of particle theory, and it has to do with collisions. The more collisions that my particles have, the greater amount of pressure is formed. Now, the first has to do with the volume of my container. Now, if I have a low volume, I have a higher pressure. So let's say I have two containers. I have container number 1 and I have container number 2. Now, in both containers, I have 2 gas particles. Now, in container number 1, because my volume is much smaller, that means I'm increasing the likelihood that my gas particles are going to be hitting each other. And if I'm increasing the likelihood that my gas particles are hitting each other, I'm increasing the pressure. Now, if I'm looking at container number 2, because my second container is much bigger, there is more space for my gas particles to travel. More space means the likelihood that they are going to be hitting is less, decreasing the pressure. So in number 1, it has a low volume leading to a high pressure. In number 2, because I have a higher volume, I have less likelihood of my particles hitting, leading to a low pressure. Second variable has to do with the number of particles. The more particles I have, the more they're going to be more likely to hit, the greater the pressure. So if I have 2 boxes that are the same, so if I have 2 particles in one box, and in the second box I have 5 particles, well, the box that has the 5 particles, it's going to be more likely that they're going to hit each other than the box that only has 2 particles. So the more particles that I have, the more pressure, the less particles I have, less pressure. So if I'm looking at these 2 boxes, box 1 has a lower amount of pressure compared to box 2, which has a high amount of pressure. The last variable has to do with temperature, because temperature is the degree of particle agitation, which has to do with the amount of energy. So the higher the temperature is, the more the agitation, the more energy my particle has. And what's really important about this is the higher the energy, the higher and faster they move. So if they move higher and faster, that means I'm going to have more collisions. And if I have more collisions, ultimately I have more pressure. Last thing is our 3 key principles of fluids, and everything that we've been talking about is leading up to this. First and foremost, a fluid naturally moves from a zone of high pressure to a zone of low pressure. And this is super important in a lot of different concepts, but really important in breathing. Because the entire mechanisms of inhaling and exhaling has to do with different pressure gradients. That when we are inhaling, our diaphragm and our intercostal muscles contract. So that means our diaphragm drops, our intercostal muscles push our ribs outwards and upwards, increasing the area, the volume in your lung cavity. You increase that area, the pressure now goes down. So that means there's a higher pressure of air outside of the body compared to inside of the body, and the air flows into the lungs. Exhaling is the complete opposite. Because my diaphragm and intercostals relax, the diaphragm pushes up, the intercostal muscles causes the rib cage to go in and down, which decreases the volume of your lung capacity, which increases your pressure, pushing your air outwards. So number 1, super, super important in a lot of biological systems. Our second, and this is called Pascal's principle, is that the pressure applied to a fluid in a closed container is equally distributed. And when we're saying closed container, that means the container does not let anything escape. And this is actually used a lot in hydraulics and pneumatics. That if my container is closed, when I'm applying pressure, the fluid is easily distributed, so I can actually manipulate how my different components move. And then our third principle is that a transfer of pressure can increase the force involved. And this is used a lot together when we're talking about car lifts, when we're talking about car jacks, or when we're talking about pneumatics. And what's really important here is this concept of multiplication factor, which is actually described in the next video in this playlist. I hope this playlist was really helpful for explaining fluids and pressure, and I hope that you have an awesome day.